and welcome to the first of 3 webinars on the topic of accounting for climate change impacts in the design of resource roads, resource road crossings. I'm Matt Kroski. I'm a research engineer at FP Innovations, and for the past 2 years or so, I've been working on, one of the things I've been working on is climate change impacts projects, especially in regards to resource roads. It's a very complex, fascinating space, and I've been working on kind of blending, putting together issues with climate change and climate change models and how that impacts design flood hydrology. So I kind of know enough about both to be able to synthesize that information in a way that is hopefully useful. I have climate change experts with me today, Kari Tyler and Mel Reasoner. Kari is a adult education specialist, and she's working in outreach as a user engagement and training specialist at PCIC, Pacific Climate Impacts Consortium. Mel Reasoner is a climate scientist that has been working in the field for well over a decade, and he has been doing a lot of work with he has a PhD from Earth and Atmospheric Scientist from U of A, and has been working with Columbia Basin Trust since their inception in 2007. And now he's working with colleagues at the Climate Services Consulting. So let's just jump right into housekeeping. If you have any questions that you would like to ask by voice, you want to click participant list on WebEx, and up pops a menu, and you can click raise hand. And we'll see that you've raised your hand, and we'll unmute you when a good time comes. And we ask that you just also lower your hand once you've asked your question. And unfortunately, if you're calling in with the phone number, not through WebEx, we can't unmute you. So you're going to have to find some other means of communicating, which I'm about to explain here. If you want to use WebEx chat, here you can ask tech support questions. Omkar Selgaonkar is online for that. And you can also comment or make any questions using your WebEx login. So everyone's going to know who you are, and you can ask that to everyone or to specific people. The way I want to encourage questions is through Slido. This way you can influence the presentation, vote on polls, upvote questions. This is anonymous by default. You can change things. You can fill out a profile, but it's not really necessary unless you want to. And also when you're once I launch polls, make sure you scroll down and hit send. It's sometimes off your screen. So I have had actually up a poll this whole time. It looks like the majority of people are feeling 4 or 5 stars today. So I'm going to pass now to Brian, who's going to give an overview of this whole issue and what we've been doing and how we built up to this point. After that, I'm going to speak for about 20 minutes, then pass it to Kari for 10. Mel's going to speak for about half an hour, and we should have about 25 to 30 minutes left at the end for any discussion.
Thanks, Matt. This is Brian Chow. I'm with the engineering branch of the Ministry of Forests, Lands, Natural Resource Operations, and Rural Development. I'm the climate change lead for engineering branch. Climate change is a focus of the engineering branch, particularly with respect to vulnerabilities associated with resource roads. This is the first of 3 webinars following on a webinar series that we did earlier in February on design flood hydrology. Coming out of those webinars, which were a bit more theoretical, there was demand for something more practical, and we've worked with FP Innovations to put together this particular series. So we've undertaken quite a bit of effort in evaluating climate change impacts to resource roads with the objective of developing and providing guidance for practitioners to address climate change vulnerabilities of resource roads. These webinars and the work that we've done with FPI is a result of work through a corporate agreement that the ministry has with FP Innovations. We've engaged with FPI doing a variety of different engineering research for the ministry over many years. We've worked with FPI, particularly over the past several years, focusing on efforts of climate change impacts to resource roads. We completed a couple of years ago 3 climate change high VCs, vulnerability assessments that were carried out in 3 areas of the province, the coast, south, and north. And these have helped to inform our direction. The work around vulnerability assessments is continuing, and currently FPI is working on developing an approach which will consider and identify vulnerabilities and climate considerations on a regional basis. And we're hoping that that will be of use to practitioners to assess for their particular areas what aspects of resource roads are vulnerable and what climatic considerations they'll need to take into account. Through the work, we've pretty much identified that floods due to runoff and from rain and rain on snow are being impacted by climate change. Design flood hydrology unto itself isn't well understood, and trying to combine design flood hydrology and climate change has been quite challenging, and we're still working on trying to find a clearer path for better guidance. These webinars are intended to illustrate how some of the climate tools and data can be applied by practitioners to address the development of design flood hydrology. I just wanted to let people know that all the work that we've done on climate change, the reports and all the presentations are posted on the BC Government Resource Road Climate Change website. This webinar series, which is also being recorded, will be posted for access as well. Back to you, Matt. Thanks.
Okay, thanks, Brian. And while you were talking there, I opened up a poll just for some introduction questions, and just to see who's attending here today. And I'll come back to results there once a few more people answer that. So like Brian was saying, this is kind of a follow-up from a previous webinar series that we did in September. And here we tried to set this up as much more practical. And 3 webinars that are going to be happening are going to kind of progress through kind of introduction of what are all the climate tools available, and then how can we start applying these through case studies, and then finally how at the end look at how we might be able to integrate data portals and bringing everything together at the end with a facilitated conversation as well. And one of the themes that I continuously was thinking about in terms of how do you make this practical? Well, let's think about if you have 1 hour budgeted to rationalize climate change, how are you actually going to do it? And so since I was given a webinar in February, the guidance document that's coming from all this has progressed a lot. It's in secondary, tertiary review by a bunch of different people. And so I'm not going to present that in detail. That should be out relatively soon. But what I want to do is just mention that over the past few months, it really, as I was preparing for this and editing this document, I wanted to really just focus in on what I mean by climate tools, because we all know what design flood hydrology is in this audience. So what I'm going to do is first define climate tools, give the context of what tools exist in BC and how these are supposed to be used then in a typical crossing, which is for smaller watersheds, and give updates on what these tools are doing and trends in how people are using them. So climate tool I'm defining here as an interactive map that shows or uses summary climate indices derived from climate models. And in a DFH context, we can help rationalize how the Q100 is going to be influenced. Q100 being the flow, the standard flow to look at on resource roads that are more than 3 years lifespan. So looking at that definition, I'm kind of using two other things that we need to clearly define. Is what do I mean by climate models and climate indices? There's a lot of resources about climate models, so I'm not going to go into it, but basically there's about 40 different global climate models that are low spatial resolution. We have governments and universities around the world working on these. They're different from each other in what kind of data they use to validate, to calibrate different physics engines. And some key points that we need to just know briefly is that each simulation has up to 4 futures that are standardized ways of looking at what's a worst as opposed to from the best to the worst case scenario in terms of greenhouse gas emissions. And lastly, there's statistical methods that can be applied that take these GCMs and make them more, enhance their resolution through downscaling. And in BC, Pacific Climate Impact Consortium does this. And at the end of the day, there's about 60 kilometer square grid that's available from 1950 to 2100 that says kind of what's happening each day with some basic temperature and precipitation metrics. There's finer grids available, but not connected to climate tools that are interfaces to these models. And climate indices are simply statistical summaries of these climate models. So here's a few examples. It's pretty obvious what these are. We're just kind of layering and seeing what's happening over time and summarizing. So the tools available for BC are here. Plan to Adapt, Climate BC Map, Climate Explorer, and IDFCC. And these I went into some pretty good detail last time around. And I just want to make a clarification here that IDFCC it's using these climate indices rather than showing them. So IDFCC, including it in this chart, is sometimes a bit difficult because it doesn't really match the other tools that are actually fairly similar in concept. And there's also a desktop version of Climate BC Map that I didn't go much into last time. And I also wanted to point out that IDFCC is available for all of Canada. The other tools are BC specific. And now Climate Data BC, climatedata.ca, sorry, and Climate Basin, Columbia Basin Climate Source. Those are two tools that sort of line up with Climate Explorer and the type of resolution and type of information they're showing. ClimateData.ca had to do a little, PKIC was one of the organizations that helped make that. And if you look at what is the actual temporal resolution that's being shown, only IDFCC is giving you sub-daily data. So if you're looking at your options here, and if you're designing a crossing in a remote watershed, it seems, upon glancing, there's only one option available, and that's IDFCC, which isn't quite true. If you take these tools and actually put them into practice, there's basically 3 different approaches to take with these tools, given the guidance, professional guides and publications that are out. The first one is you can use IDFCC. And Engineers Geoscientists BC says, you know, listen, you have to just be aware of the downscaling and the stationarity. And that just means that the stationarity means that the subdaily and the daily relationships that have been mathematically derived, that those stay constant into the future. So they say, you know, watch out when you're using this tool, but actually it really applies to using any tool or thinking about any tool when you're working at such low or high temporal resolutions. The second option is to use other tools, but with the assumption that the magnitude and direction of averages for precipitation are correlated with increases in intensities of storms. And there's a Engineers and Geoscientists BC guidance document that basically spells this out, but it doesn't highlight that, kind of like in using IDFCC, that, you know, watch out, there's a lot of assumptions there as well. PKIC recommends to look at 24-hour climate indices rather than subdaily due to the lack of data that is really there to build up any kind of case for the subdaily indices. And the last approach you could take is use no climate tools at all, at least not directly. And this comes from an Engineers Geoscientists BC guidance document that says if you're in a small watershed with little data, then you can account for climate change by increasing an additional 20% to flow. And the context there is a rural development, not forestry. So let's take a look at what happened in that first poll there. Who do we have here today? All right, so lots of crossings designers, mostly in BC, mostly public. This is a bit different from last time when we had we had more from the private sector, different from the February webinars. And yeah, lots of newcomers as well. I'm going to start another poll. So given all the information I just said, how do you account for climate change in resource roads? We'll come back to that. Just quickly, steps of using a climate tool. Very simple. You want to define all these input parameters, the GCMs, regional concentration pathways. That's the from good to bad scale with the greenhouse gas emissions, and you got to define your historic and future time periods. And we'll see these steps in action when Kari and Mel go through some tools. Define the location, select from the output those that are affecting design floods, interpret, and then compare to other methods, other tools. Defining futures, you want to, there's four, if you have to work with individual GCMs, those are four that are recommended by Engineers Geoscientists BC, but generally you want to work with ensembles, but they're not always available. 4.5 and 8.5 are the RCP scenarios that are most common. That's kind of the mid and the bad range. And time periods, those are 30-year periods most commonly. So 15 years around 2055 and 2085 are commonly looked at. Define location, different for different tools in terms of what you're doing. And then using indices. Here I have some indices. This is an excerpt from the guidance document that just summarizes what's the temporal and spatial resolutions of all these underlying indices. And there's no exact correct indices to look at here. For example, in Climate Explorer, we have the yearly max daily precipitation and the 50-year return period max daily. I'm not sure which one would be a better measure for or a better proxy for what you're expecting in terms of how intensity is going to change in the future. Lastly, calculate and compare. And only plan to adapt gives you the actual percent change. All the other tools, you're getting basically a historic value and then a future value, and then you can derive your change from there. Let's hop over to the poll question. So we do have people using primarily climate tools, and followed by not designing, and 20% more flow, no tools is the next one. So that would be that 2018 Engineers Geoscientists guidance document. And just quickly some updates. So I don't have to talk about plan to adapt. Kari's going to cover that. Also the bottom two there, Mel's going to cover those. So I'm left with Climate Map, PKIC, Climate Explorer, and IDFCC. So in terms of updates here, if you really want to be following updates, you want the desktop application. Since I've been looking into this stuff, I don't think I've ever seen an update to the web app. But lots of updates, maybe every few months, to the desktop application. And right now, they're also, I was talking to Dr. Wang from UBC, who builds and maintains this tool. They're working on taking some of the daily Climate Explorer data and making it, right now, this is something that Mel's going to get into, but if you're in a 50-kilometer cell, a grid, within that grid, it's an average value for things that you're getting. But if you account for elevation in there, it'll make the actual value more realistic. So they're working on something like that to enhance the value of the daily data from Climate Explorer. In Climate Explorer, one recent development was from MODI, and the Ministry of Transportation there in BC, that they're largely were funding and continue to fund the developments in Climate Explorer. And in this latest publication, in the appendix, there's a lot of information that was previously undocumented. So that's one to take a look at if that's a tool of interest to you. And also, we're using this tool as part of some vulnerability, regional vulnerability assessments, and that's something that Brian was already mentioning up front. And lastly, IDFCC, there has been a lot of new publications that really clarify what's going on under the hood of this tool. It's fairly complicated, all the different math and statistics going on, but these two new publications are very useful. And another thing I know that they're working on is looking at what if we don't assume that they're stationary. So if the sub-daily to daily ratios do change. And right now, from what I understand, when they're looking at that, it's a lot of computation, but they're not seeing much effect at the end of the day. But it's still, I think, I'm not sure how preliminary those findings are. And lastly, trends in climate tool use. And this is one that I got some, we don't have much data on this, and DFH in general is quite mystical in a lot of ways. And let me just, I'm going to start another poll here, which is the use of tools. So I have one question for designers only and one question for everybody.
Matt, do you want to repeat the instructions for doing the polls on slido.com?
Sure. So you just want to go to slido.com and you want to put in hashtag FPI. And as soon as you do that on your phone, any browser, on your computer, it'll, as soon as I activate one of these polls, it'll pop up. Thanks for that, Kari. I don't know if I mentioned that or if I mentioned it succinctly. So I'll just keep that poll open, and let's just go to just a few more slides here in terms of trends that are being seen at Modi. And so they break up the BC province into 3 regions. And the highest increases we're seeing is in the southern interior region in terms of bridge designs. So this is up to 20% increase in flow. And the way that they're collecting this information is fairly general. It's just a sentence saying, how are you rationalizing climate change? What data sources are you using? There's not much information or nothing formally collected about, what RCP values are you using? Which exact tools are you using? So that's kind of the types of questions that I hope that this work and these webinars will get people to think about more, and it kind of gets out there and gets discussed more. And lastly, for culvert designs, these are slightly more in terms of flow that they were documenting, and that's in the northern region and in the south coast region, up to 25%. Okay, let's take a look at which tools do you use to account for climate change in your crossings designs. So overwhelmingly, we have designers using IDFCC, but a lot of other tools as well. And yeah, and in previous webinars, I guess I was really focusing on just a rain dominant flood, but if you have other factors going on, and that's what we'll see in some of the case studies, not just intense rain, then using only IDFCC is no longer an option. Do you ever use climate tools as a source for historic precipitation values? So this is, I threw in this question because I was really focused on, when I was looking at this, I'm always thinking, okay, how much did the flow change? That's what the climate tools, which I was formerly calling climate change tools, that's what they tell you. But kind of speaking to more and more designers, a lot of times these climate tools are arguably a better source, or the best source, for information about what's the actual historic precipitation, for example, at a certain location. And with the other alternatives being old contour maps for different IDF charts, or different IDF values. So there's some people that are starting to use these tools kind of for the full process, and of course probably cross-checking with other methods. But that's an interesting one to know. And that's where I'm going to leave it off. And I want to pass it to Kari, but maybe just before I do, I'm going to activate a number. That's simply, have you used Plan to Adapt? We have a few veterans. Okay, good. We're getting a lot more people voting now that people are used to Slido. So maybe, Kari, it's good that you got me to explain that again.
Yeah, and now that people have figured out Slido, the other thing that I wanted to draw people's attention to there is that Q&A option. If you look at the top of if you're using a browser, there's polls and there's also a Q&A. So as you have questions, tough questions for Matt as he's done his presentation, or questions for any of us, you can put them in there, and then I think that gives us a good space to start when it comes to the discussion at the end. So that's really helpful for us. Yeah.
So right now, I don't think we have any questions yet, but put anything in there. And so we can probably switch now to your screen, Kari.
You know what? I thought I was able to click on the share content button.
I think Omkar can make you, I think Omkar, here we go.
Oh, now I got it. Thank you. All right. So I might just have to change the view when I start this because that always happens. There we go. Okay, so hopefully you guys are seeing what looks like a landing page and not my presenter notes or anything like that. Is that right, Matt? I can only see your face.
I'm seeing your presenter notes actually.
Oh, are you?
So maybe just need to switch the view there in the top right.
Okay. What are you seeing? This is right?
Yep.
Okay. This is interesting. I did a presentation yesterday and the screens that it defaulted to were the opposite ones. So I am glad that I asked. Okay. All right. This is going to be quick. I mean, really, there's a part of me that's like, I could just stop with this title slide. The main message that we wanted to come to you guys with today is that Plan to Adapt has been updated. So the main thing here is so now Plan to Adapt has been updated. It's using this CMIP 5 models, and part of what that means is there's now daily data, but Plan to Adapt has really been designed as a fairly simple and user-friendly climate tool. It's sort of the peak best guess at if you had 5 or 10 minutes to get your hands on something that would give you a bit of information that's relevant to your region about future climate, what's a really easy way of doing that. So of the range of tools that Matt was discussing, Plan to Adapt is really considered it's intentionally designed to be the most user-friendly. So if you compare it to the Climate Explorer and stuff like that, part of what this means, there's fewer variables, regions are predefined, it already is calculated using an ensemble, and all of the projections are using RCP 8.5. I just wanted to do a very short reminder of why it is that RCP 8.5 is what's being used, and that's basically because if you think about, so RCP 8.5 is the red line on this image, and mid-century, this red line is, so the amount of climate change that you see in the 2050s under RCP 8.5 is comparable to the amount of climate change you would see under RCP 4.5, which is the yellow line, in about the 2070s. So for sort of getting a place to start for decisions in the 2020s or thinking about the 2050s, RCP 8.5 is a good place to start. That's why we're using it. Just quick, the features that we've got on Plan to Adapt are fairly simple. One of the novel things is an impacts tab. That's probably less useful for this audience, but it's a useful thing for people that are sort of brand new to the climate conversation to just think about. It opens up questions that they should be thinking about in terms of impacts to climate change. So if you go into the tool, there's some things that you can choose to get some simple information. These regions are predefined and they've broken down into regional districts, health authorities, and eco provinces. You can pick the time period that you want to be looking at for your climatology. And so here's an example of the summary page that you would get if you were looking for mid-century in the Kootenay Boundary Regional District. So what we have are seasonal and annual indicators for just a handful of variables here. And I think I still do think that Plan to Adapt is a useful place for you to start, even if you're thinking about stream crossing, because one of the points that's important here is to remember the way that temperature drives a lot of changes. So in this Kootenay Boundary region, for example, this shows the change in frost-free days, which would have a big impact in snowpack. and so would, this is now just a graph to show the graph feature. This is the change in temperature in the spring in that same region. And this does just show the change in temperature. But if you're familiar with the historical values of the baseline, the historical temperature in this region is just below 0. And so part of what that means is that as there's warming in the spring through the coming century, that is going to mean that the sort of average spring temperature moves from just below 0 to just above 0, which again has a really big impact on snowpack. I think it was just below 0. I was looking at more stuff about this yesterday. The nighttime low for sure was just below 0. So the spring average temperature would be higher than that. Anyway, so plan to adapt is sort of a quick, easy intro, and part of the questions that it answers is what should I be looking at more closely? And also, I hope that when you're thinking about crossing design, that part of what you're thinking about is how much is temperature changing overall in this region, and then it's kind of on you to think through a little bit more, what does that mean in the nuances of the drivers of things that would affect stream flow. So this is just the screenshots that show the available variables on plan to adapt and the annual and seasonal data that's available in the maps. And I wanted to make this really quick so that we had lots of time for Mel and discussions at the end. If you have questions about plan to adapt, you can always email me, and I will probably rope in some colleagues that know more about the details and the behind the scenes bits of plan to adapt. But the big news is that this has just been updated. The graphs feature was just added today, and there will be there will be some additional changes and improvements, and I'll be doing some more work in the coming year to look at things like the what's behind the impacts tab. So there will be more changes coming with plan to adapt, but the biggest thing is we have this new version with the CMIP 5 up and running, and so it should look and feel a little bit different than the old one, and hopefully that'll work for people. I think that's it for me.
Thanks, Kari. That was great. And yeah, I don't know if we have any questions off the bat or if we can wait till the end with that. I don't see anything in Slido.
Okay. Yeah, so I will just remind people, feel free to either email me with questions, ktyler@uvic.ca, or put questions into Slido. One of my pitches for putting questions into Slido is that, you know, as your teachers always said in school, if you have a question, there's probably someone else here that is also thinking of that question. So if you can be the brave one to put it forward in words, others can respond and upvote it. And that gives us a really good sense of sort of what's on people's minds. So if you do have questions, please do put them forward in Slido. So.
All right, great. And I just put up another poll up in Slido, and this is just about have you used the Columbia Basin Climate Source Tool and have you used climatedata.ca. And I think we're not going to go to my screen. I'm just going to read those results out, and we can pass the presenter role to Mel. And I think we're right on time with what we were aiming for so far.
All right, Matt, I'm just waiting for, oh, there we go. Now I'm activated. Hang on a sec here, I'll get my presentation up.
Okay, so we have 26 respondents so far for have you used Columbia Basin Climate Source Tool, and 90% have not. And as far as climatedata.ca, 64% have not, 30% just a bit, and only 7% lots. So I think that gives us a general lay of the land there for how familiar people are with these tools.
Okay, Matt, are we good to go?
Yeah.
All right, well, thanks very much, Matt, for inviting me to take part in this webinar series. As Pat mentioned, I've been involved with the Columbia Basin Trust since about 2007 when they started their climate action programs. So I've largely come to this point in my life as a user of climate tools. And for a long time, the only thing that was really available was PKIC's regional analysis tool, which was affectionately known as the RAT. And they freely admit that it was rather user hostile. So it's really good to see all of these new climate model projection resources coming online. Now I'm not going to go into too much detail of these because because it's largely been covered in previous webinars and also just earlier today. But I do want to start off with a couple things to watch out for when using these tools. There are some potential pitfalls, and I think that a lot of folks will probably be aware of these, but I also am aware that some people have been charging ahead with these numbers without placing them in context. So I'd like to start this with an example using Nelson, BC to illustrate some of the issues. And here we go. So first of all, in Nelson, BC, there are some climate data available, some historic data available, but it's not great. You can see that there's fairly large gaps. But this is the case in many parts of British Columbia. You don't always have great data where you are. One of the tools that Matt was alluding to that has high quality historical data that's very high resolution. It gets down to 800 meters in terms of resolution. And this comes in very handy for sort of calibrating your local climate history if you don't have great local data. And there are monthly time series available from 1950 to 2007. And when you map that onto the local Met Station data for Nelson, you get a pretty good correspondence between Environment Canada historical climate data and the PRISM data. Now, if we look at this period, 1951 to 1980, which is a common base period used for model projections, and with both of these, you end up with a mean annual temperature for Nelson from 1951 to 1980 of about 8.1 degrees Celsius. Okay, keep that number in mind. Then if you go to climate normals for Nelson, this is the 1961 to 1990 baseline, but only 10 years off from the previous. And there it's 8.2. So that corresponds fairly well with our estimate for 1951 to 1980 mean annual temperature in Nelson. And now when you go to Climate Data Canada, which has first of all, it has a lot of really great ways to get your hands on climate data and to plot graphs, and I'll be showing a couple of those. But when you go to Nelson, the location Nelson, and the first thing that it gives you when it spits out the information is for the 1951 to 1980 period, the annual average temperature was 4.5 degrees Celsius. And we've determined from Met stations in the valley bottom that it's actually 8.1 or 8.2 degrees Celsius, and that's a big difference. And when you start digging into the different climate variables that are available for historic and projections from Climate Data Canada, this offset propagates through all of the indices. And for example, here we're looking at projections of maximum hottest daily temperature for Nelson, BC. And you can see that according to the model projections and the information that you get directly from Climate Data Canada, you're never going to exceed 40 degrees Celsius in Nelson, BC, even by the end of the century with the worst case climate scenario. And that's not the case. And if you've got infrastructure in Nelson that's sensitive to very high temperatures, then this is inaccurate. And in fact, we sort of got onto this working with a local MOT engineer a couple of years ago, and he was responsible for bridges in the Nelson area. And one bridge had a threshold for its expansion joints around 40 degrees, and it failed in the summer of 2015. So the chances of exceeding 40 degrees Celsius in the near term in Nelson are actually quite high, and you should not be taking these numbers at face value for this location for future projections. So what's going on here? What I'm going to do here is just pop out of the PowerPoint, and now I've gone to the Columbia Basin Climate Source. And this was something that our kickoff meeting for developing this was 2018, and at that time there wasn't a lot of other online availability for projections. But of course, while we were getting this up, a number of the other sources for climate information did pop up. So if we're looking at mean annual temperature in the grid for the Columbia Basin. It only covers the Canadian portion of the Columbia Basin. Now, just to illustrate what's going on here with this, if we zoom into Nelson, you can see that here's the grid square that has Nelson in it. There's the town of Nelson, and you click on this grid square and you get 4.74 degrees Celsius. So that's very much in line with what Climate Data Canada is saying. The problem here is that the valley bottom temperatures, mean annual temperature for that base period, 1951 to 1980, are reflecting the valley bottom temperatures in this grid square of 60 square kilometers is incorporating cooler temperatures from higher elevation. And so you've got to bear this in mind if you're dealing with temperature. Anytime you're looking at the projections, they're giving you the average in a grid square, which can be cooler than your valley bottom locations. And in BC, this is an issue. In Saskatchewan, there's not much of an offset. But I can very easily illustrate this. You can see there's quite a bit of high elevation in the Nelson grids, the grid square that Nelson is in. But if you just scoot over here a few miles to Crawford Bay, this grid square has a little bit of elevation in it, but a lot of it is at the elevation of Kootenay Lake, which is the same elevation as Nelson. You click on that grid square and you get a mean annual temperature of 7.7 degrees Celsius, which is more in line with what we see at the Met stations in Nelson. So, the difference between Nelson and Crawford Bay has got nothing to do with climate. The climate's the same essentially. The difference between these two numbers is reflecting that the fact that this grid square is incorporating more elevation and therefore cooler temperatures. And again, that's propagated through all the model projections. Okay, I'll pop that back into slides here. And then talk a bit about precipitation. And just in general, the climate models do a really good job of projecting temperature and replicating past temperature history, but it gets a little tougher with precipitation. And here we're looking at Barrier Lake, Alberta, which is close to the Kananaskis Weather Station, which is in the headwaters of the Bow and the Elbow River, roughly. And what goes on in the headwaters of the Elbow River is really important to what happens downstream in Calgary. And here you can see 2005 and 2013 were really big flood years in Calgary. If we go up to the headwaters and have a look at this, the history and projections of one-day rainfall, maximum one-day rainfall at Barrier Lake, here's the model projections, here's the model climate history, and here's what the climate station looks like. Most of the years do fit in with the envelope of modeled history, with two big exceptions, and those are the two big flood years in Calgary, 2005 and 2013. And just for reference, here's another one, 2014, and we'll have a look at that in a second. Another example, quickly, is Kaslo, and there's the modeled history of projection, and here's the Met station in Kaslo, and there's a bit of an offset here between the two, which is interesting, but even if you line those up, you still have that one big year, which was 2013. It was the same storm system that went through, and it exceeds anything that's in the model projections. But interestingly, 2005 in Kaslo was way down here. So in one case, you've got that storm system influencing both Kananaskis area and Kaslo, but in the other case, you've got the 2005 event only showing up in the Kananaskis region. And lastly, again, 2014 at the bottom, we'll pop down to Waterton, Red Rock Creek. So this forms sort of a nice geographical triangle. And here we're looking at modeled history and projections. And here's the actual Met station at Red Rock Creek. And again, it's a shorter record, but most of the years fit in are close to the historic envelope of model history. But there's this one big peak. The problem here is that's not 2013. There's 2013. This was a 2014 event that didn't occur in Kaslo or in Kananaskis. So the takeaway message here, there's two of them. One is that, especially with extreme precipitation, it's very spatially variable. There's a lot of spatial variability. And in many cases, what we're seeing is that the historic observed RX1, or maximum daily temperature, exceeds model projections. So the conclusions, the takeaway conclusions here are, okay, there's lots of online data now available with all of these climate sources, online climate sources for projections that have been discussed, for historical and for projections. Some of the functionality is not working, but there's new functionality becoming available all the time, and Carrie just outlined what's going on with Plan to Adapt. But the key messages here are, in regions of high topography, the temperature information should be interpreted with caution. The historical and projected data represent 100 or 60 square kilometers around your community. With the Climate Atlas, it's actually 1,000 square kilometers. And that does not reflect what's going up at the valley bottom. The absolute numbers that you get from these sources, therefore, may not be appropriate for community planning. The change in climate indices relative to the base period is the key information. That is solid, especially with temperature. So what you need to do, especially with temperature, is get your hands on as much data as you can if you're interested in absolute temperatures in the future, and do your best to adjust things to the actual base period temperatures at your location. With extreme precipitation, again, this should be interpreted with caution if you're just getting those numbers directly from the sources. In many cases, the observed one-day temperature exceeds model projections, and these may not be appropriate for community planning. There's really good scientific justification for assuming that extreme precipitation is going to increase, and this has been observed globally, but it's a tough one. It's much more difficult to estimate the absolute magnitude of the changes in extreme precipitation. And again, the best approach is to get your hands on as much historical data at your location as possible. Place it in that context. All right, what I would like to do now is pop over to a quick demonstration of a tool that we've been developing. We're calling it Localized Climate Analysis and Projection. And I'm just going to jump onto that website. Here we go. And this has been developed by Climatic Resources Consulting, and that's Charles Coelho and myself, who started this up a few years ago. And what we've done is we've got a diagram on the left that looks very similar to what you would be able to get your hands on from sites like Climate Data Canada or the Climate Atlas. And it gives you a time, or the Climate Explorer. It gives you a time series going forward, and it gives you the historic temperature record. In this case, we're looking at mean daily temperature. One of the differences right off the bat is what we've done is this blue data is actual data from Kaslo. There's a high quality Met station in Kaslo that's got lots of good data, and we've adjusted the models over the base period to that actual valley bottom data. So this is very much localized to valley bottom conditions. But then what we've added to this graph that gives you a sort of a qualitative idea of how things are going to be changing in the future is, based on this information, we've developed a probability plot over here on the right. And so our threshold here is 10 degrees Celsius. And what we're seeing on this lower plot right here is the annual exceedance probability of exceeding 10 degrees Celsius at Kaslo. So basically, this is telling you that by about 2050, there's a 27% chance that you're going to exceed 10 degrees Celsius in any given year. And so that gives you the annual exceedance probability as you go forward through time. And the second plot that we've got is what we're calling the accumulated risk. This is up here. And what this tells you is the accumulated probability of exceeding 10 degrees Celsius at least once before 2050. So these two probabilities will answer different questions. If you've got something that operates on an annual budget, maybe it's cooling degree days and it's related to annual cooling costs, then this annual exceedance probability is of interest. But if you've got a piece of infrastructure, a crossing, for example, and you're worried about whether it's going to get blown out, or let's say I'm talking about mean temperature here, so there aren't really great analogies for that. But if you've got some infrastructure that was sensitive to 10 degrees Celsius mean annual temperature, this tells you the likelihood of that happening before 2050. Okay, I'm just going to quickly pop over to highest maximum temperature just to work through a couple of examples. And this just takes a second to fire up. While it's doing that, there are a bunch of indices that we've got that can be looked at, and many of them are common to what you can look at in Climate Explorer or Climate Data Canada. So now we pop to highest maximum temperature. So the threshold that we've got is 40 degrees Celsius, and it's telling us that by 2050, there's a 57% chance, even though it's never happened in Caswell so far, there's a 57% chance that 40 degrees Celsius will be exceeded once by 2050, 56% chance. Okay, so if another situation is, for example, say you want to know what year you run into trouble with your infrastructure. And if your risk tolerance is, say, 20% instead of 50%, so we'll enter 20 in your risk tolerance, and your threshold is, let's say, 42 degrees Celsius, or 41 degrees Celsius, and we 41, hang on a sec, 41, enter, and now we calculate. What it will do is then calculate the year that there is a 20% chance of exceeding 41 degrees Celsius. And it's just thinking about it. This should give us another stop year. Is it saying 2050? It is. Okay, that ended up being the same. We'll try another one. Let's say we're looking at your threshold, your design threshold, and you're planning for 2070. Whoops. 2070, we enter that. And your risk tolerance is, let's say, 15%. It'll then calculate at 2070 what, oh, heck, I've done this wrong. In any case, I'm blowing here, unfortunately. Risk tolerance 0.2, enter. And it should, what this should do is tell me what the threshold is in 2070 if my risk tolerance is 2%. And last time I did this, I got 43 degrees Celsius. So I hope this allows you to see how this works. And obviously I messed up on the last one, but essentially what this does is it will establish a threshold, and you can calculate the year along. If you establish a threshold and your risk tolerance, it will calculate a year, or if you establish any two of these, it will calculate the third and give you a probability of exceeding that threshold. All right. What I'll do now is pop back into the slideshow here. And what we ended up doing is teamed up with Kim Green, who's a local geoscientist with a consulting company here in the Kootenays, Apex Geoscience. And she has specialization in hydrology and fluviogeomorphology. And Kim has done some extensive work in what we're calling John Doe Creek, and it's in the Nelson region. And we decided to see if we could just start to see how this approach, the LCAP approach, could be applied to this local watershed. And in this case, there's concerns around the increased frequency of overbank floods and debris floods that may lead to increased occurrence in culvert blockage and intake damage, and increase in channel instability causing damage to infrastructure and private land. So the first thing we did is we went to, when we really want to localize the climate data. So there is some climate information from the Nelson station, but with John Doe Creek, there's very little flow or discharge information. There's only about 6 years, and it's fragmentary. But there's enough to work with, and I'm looking at 47, and here's the discharge in John Doe Creek in meters cubed per second, mapped on top of the precipitation. And I chose the one bit of information that runs later into the year, into August and September, because it allows you to see the sensitivity of John Doe Creek without, in the absence of a spring freshet. So you get a pretty good kick in terms of discharge when you have a rainfall event of above 25 millimeters in a day, and even some of these smaller peaks in rainfall, when there's a few days in a row, will give you a bump up in discharge. There's a nearby creek that has a great record, and that's Anderson Creek. It's less than 10 kilometers away. And there's the response in Anderson Creek compared to the response in John Doe Creek. And I think they're remarkably similar. And this then gives us the confidence to use Anderson Creek as a proxy for what's going on in John Doe Creek. So here's the Anderson Creek record, and it's fairly complete. It goes back into the 40s, but I'm starting it here in 1969. And this is discharge for all of those years. Very little missing data. And I've just chosen a threshold above 1.5 cubic meters per second. And there's 8 peaks that stand out. There's 71, 72, 97, 99, 2002, 06, 12, and 18. And I'm going to look at 4 of these in detail. The highest 3, and then the one that's tied for 4, to tease apart what's going on and what's driving these high flow events. The other thing that's convenient about this situation is in between John Doe Creek and Anderson Creek, there's a snow survey that's located at about 900 meters, which is sort of lower mid-elevation of both drainages. And these drainages are very similar in size, aspect, and elevation. They're fairly comparable. So here's the snowpack information. And what's interesting right off the bat is you can see that some years, like 97 and 99, which were big flow years, are associated with a high snowpack, May 1st snowpack. But some years that have, really high flow, like 2002 and 2006, are associated with years that don't have really high snowpack. So snowpack is a factor, but it's definitely not the only thing that's going on here. But one thing that is clear when looking at this is that most of the years that have 0 May 1st snowpack, most, not all, but most of the years that have 0 May 1st snowpack also have low discharge. Those 4, for example. This one's a bit of an anomaly, and so is this one. Okay. The other thing that's clearly happening here is when you look at May 1st snowpack, it's declining. There's a trend here with May snowpacks at about 900 meters elevation is definitely on its way down, and it's probably going to be very common to be very low in the near future. So I'm going to start looking at the four events starting in 97 to see if we can tease apart what's going on. So on the right, we've got from April 1st to June 30th, the discharge in blue and the temperature in green. And on the left, we've got the precipitation, precip in orange and discharge in blue. And you can see there's one peak in late April that was about 30 millimeters, and this is 2-day rainfall. This is RX2. This is total of rainfall in 2 days. So a couple of days around 15 millimeters, and that definitely had an influence on the discharge. And there's a little peak with several days of rain a little bit later. But when you look at the main peak in Anderson Creek in 1997, there really wasn't anything going on with rainfall. But if you look at the temperature record, it becomes clear what's going on, is that temperature was relatively low up to about a week before the peak event, and then it ramped up into the mid-20s immediately before the peak discharge event. And what I've done here is I've taken the 7 days before and taken the average temperature, and the 21 days before that and taken the average temperature, and that's at the bottom, and you can see the difference is 8.5 degrees Celsius. And this is a metric that we think we'd be able to use for quantifying how heat and snowpack work together. And it's directly analogous to an index that was developed in Australia for the health sector with heat waves. They noticed that with rapid onset heat waves, the hospitals would fill up. And if there was a more gradual onset, there would be acclimatization. And there's sort of an analogy here. Had the temperature warmed up more gradually to the peak, then the melt would have been slower, but more consistent, and it would have sort of flattened out the discharge curve. It would have flattened the curve. So when you have the situation where you get a rapid jump into your heat wave, this is where you bunch up the discharge all into a peak, and it overwhelms can overwhelm the culverts and crossings, much in the same way that hospitals can be overwhelmed by a peak in COVID. But this is one metric that we're looking at, this difference between the antecedent temperatures and the temperatures during the heat wave that is associated with the discharge event. And in this case, it's very clear that there wasn't much going on in the way of precipitation. We fast forward to 2002, and you can see, the difference in this case between the week before the peak and the 3 weeks before that is actually negative. It was warmer during the 3 weeks before than during the week right before the peak. So it's clearly not temperature that's driving this peak. And when you look on the left graph, it's clearly precipitation that was driving this peak. So there's clearly more than one way that you can the climate, or weather, I suppose in this case, weather can drive a runoff peak. So in this case, in 2002, this was also a major flow event in John Doe Creek, and in 2002 it was documented that there was a culvert blown out during this flood event, which was in this case clearly driven by precip and not by temperature. Fast forward to 2006, and in this case again there's not much going on in terms of precipitation. Maybe the latter part of the peak was helped out a bit by a few days of rainfall, around 10 for RX2. But again, what was clearly going on here is that relatively low temperatures followed by a rapid jump up into a heat event immediately before the freshet. And that difference in this case was plus 7.5 degrees Celsius. And lastly, looking at 2012, again, it's not temperature. The temperature was declining into the freshet event, but when you look at the rainfall event, it was a huge peak, 70 millimeters of rain in 2 days that was clearly driving this particular discharge event. So when we come back to looking at Anderson Creek, the data from Climate Data Canada, and you compare that to historical in terms of RX1, you can see that what we've seen already is that there are some events that are in excess of what the models are projecting. So what we've done, and it's not dissimilar to what the IDFCC tool does, is we take the observed distribution and we fit a generalized extreme value curve to that data. We do the same for the models over a calibration period. And then we look at the change in the parameters for those general extreme value distributions going forward in the models. And then we add that change in the model distributions to the historic to get the future projections. So in that way, it captures the variability, the historic variability that's present in the local data, and it maps onto that the variability and the change in trend of the model data to get an estimate of what future RX1, future RX2 would look like. And to cut to the chase, here's the probability graph for an RX2 event exceeding 70 millimeters at least once in the future. And so if we look at this, by 2055, there's about a 6% chance of this happening again in Anderson Creek. This is a good analogy for John Doe Creek. But this is only one part of the story. So to put this in terms of crossings, if you're comfortable with a a 6% chance of your crossing being wiped out before 2055, then you're okay. If you're only happy with a 2% chance, then there may be a problem. But again, this is only part of the story. This is the RX2 part of the story. And there's also heat waves and snowpack. And heat waves in RX2 are probably independent. It's hard to get a heat wave in April and May when it's raining like hell. But there is some interdependence between snowpack and heat wave, which makes it a bit more of a complicated problem. But in any case, it's doable, and we can come up with probabilities for these events, and they're given as the probability of exceeding a threshold at least once within a given time frame, and this influences the flow. And the goal here is to come up with probabilities of damage within the time frame of interest. And lastly, using Bayesian statistics, the probability damage it'll be a distribution with a plus minus attached to the probability value. Now, Bayesian statistics versus frequentist statistics is a huge long-term war that's been going on in the statistical community. And Charles Coel, who's my colleague, is employing Bayesian statistics to generate these probabilities. And the best analogy I have for that is that a frequentist, if he loses his cell phone in the house, would have a mental map of the house and would go to each room and spend an amount of time proportional to the size of the room searching the house for the cell phone. Whereas a Bayesian statistician would take that same model, but also incorporate it into it, the knowledge of where he usually leaves the phone, and start looking, beside in the bathroom, beside the sink, or beside the kitchen sink. In any case, those sorts of details we're happy to discuss in more detail, and we could be contacted at Climate Resources Consulting, and my email is at the bottom. And I think I'm pretty close to being on time, so I'll wrap up there.
Thanks a lot, Mel. Yeah, I think that's a great presentation that really goes to show the other types of climate indices that we need to start thinking about, especially compared to the last webinar series where we were only talking about intense rain. I'm going to throw up a poll based on this risk and probability topic that Mel went into, in terms of is looking at those graphs in terms of probabilities and risk. Is that something that's useful? There's two questions there. We can come back to those. And I also saw a few questions for you, Mel. We have many resource road crossings are not in valley bottoms, but at elevations. Do the cautions that you mentioned apply at elevation?
I think so. If you're partway up the mountain and you've got a met station in the valley bottom and you don't have data at your location, then you want to try to find some way of backing out what the historical conditions are at your elevation. For temperature, there's a couple ways forward. If you've got a met station in the valley bottom, you can sort of use an environmental lapse rate to estimate that, to adjust. And another option is to use PRISM. PRISM is pretty good. It gets down to 800 meters for historical climate. So for temperature, yes, there's ways that you can dial it in pretty good to come up with the likely baseline climate for your location, regardless of the altitude, and then make adjustments to the models accordingly. With precip, it's a thorny problem, especially with extremes. The best thing to be able to do is to look within your region to see, have there been really big extreme events regionally, and then see if those exceed model projections for the closest location. And then, treat those extreme precip events with a grain of salt, unless you're able to use a tool that involves incorporating the observed variability into the future, which with RX1, the IDFC tool does that, and there's different ways to skin the cat, but it's something that can be used to deal with that problem.
Okay, and another related question to the LCAP tool. Is there a way to get an error band around the 57% chance of 40 degrees being exceeded? That's a pretty precise number. what are the possible ranges?
I think that that's something that Charles is working on. I think in the last slide, the probabilities will.
Hi, this is Charles. Mel's had been having troubles with his internet, it seems. And we lost you there for a second.
Oh, sorry.
Yeah, no, we could definitely get error bands. We don't have it incorporated into the UI yet, but I have been working with those already.
Okay, and another question about LCAP. Is it freely available?
At this point, no. Our first client is the City of Edmonton. They've purchased it. And we're also using it as in-house software for consulting work that we do. That's where we are right now, at least for the foreseeable future, in the short term.
Okay. And here's a question for you, Mel, or maybe Kari, you might know, do any of the climate tools, or maybe I might expand this to climate models, include a metric for cloud-free days as it relates to solar radiation and watersheds? So people are starting to think about all these different metrics that we have and how we might combine them, and how different watersheds might have different amounts of these indices that to take into consideration or not. So either of you have a comment on that one? I haven't seen that in any tools, but maybe in the models.
I haven't either. Kari?
Yeah, I haven't seen that. I think I don't know. There's a couple of my colleagues that I think are attending. I don't know if anyone wants to chime in the chat just to sort of address some of the challenges with clouds and the climate models, but we will see. Yeah, I don't. There are no existing tools that address cloud-free days, and I don't think it's something that would be likely in the near future. The explanation of the why is sort of beyond my technical knowledge with the climate models, but anyway, I don't think it's a thing that will be available as a tool component anytime in the next 5 years, let's say.
All right, thanks. And just coming back to the answers to the polls. So the first one, have you done work in the past where you feel you relied too heavily on qualitative assessment of probability? 40% say yes, 30% say no, 30% are unsure. And do you feel that a more quantitative assessment of probability could have been applied to past work, but you lacked the tools? Yes, 75%, not sure, 25%, and nobody said no. So some good feedback for you're onto something there in terms of converting those graphs into probabilities and risks. Okay, now I saw a few other tools. One from a while back is the 20% added to Clearflow only. Does it account for debris and sediment bulking? Now, I'm not sure if that question was about the 20% for the engineers geoscientists guidelines, or if that was for some of the figures that you were seeing in the MODI results for how designers are designing increasing flow. As far as the guidance document, that 20%, I don't know what that 20% is supposed to really encompass. It seems to me like it doesn't really directly account for debris. There's no step-by-step documentation or rationalization of how that 20% was decided upon. It just kind of emerged from a body of experts of climate scientists and engineers. But in terms of dealing with debris, I don't think people have thought about that enough, and maybe again it has to do with getting into more of these indices, of which ones are important, how to combine them, how to think about them together. Yeah, I don't know if anyone can put into Slido any thoughts on that, or how people have dealt with debris in terms of just using historic record, let alone how that changes into the future. It's a difficult problem. I saw some other questions in the chat there. So this is for you, Mel. In the Anderson example, does the precipitation likelihood prediction by your tool take seasonality into consideration? For example, a 70mm event will likely only result in flooding conditions if it occurs during the spring freshet. So future likelihood should be constrained to occurrence of a 70mm event during the spring.
Yes, we can do this seasonally. That would be a very easy modification to make.
All right. And we have another question. Have you tried incorporating an uncertainty assessment of these tools? I'm not sure which tools that's referring to, but in terms of, it kind of comes to a good point. I don't know if this is what the question's getting at, but anytime you're using any of these tools, you really need to be thinking about a sensitivity analysis. So whether that, whatever that means, especially if you're kind of first coming into these tools or first coming into a particular geography, what is the difference that our RCP 4.5 versus 8.5 makes? According to EG Engineers Geoscientists BC, that's something that you really should do. They're not saying that you can't pick 4.5 in the end, but you could, you should at least consider it. So if that's what we mean by uncertainty assessment, that's definitely something to focus on. Is you're getting these ranges of answers, and a lot of the ultimate judgment that you're bringing forth as the designers is how you're interpreting that band of possibilities. Okay. Mark, have you seen any other, did I miss any questions on the WebEx chat there?
No, I think you captured them.
Okay. And Jim, I think you're online. I think you said you might want to make a comment on some of the slides that you provided for here. Not sure if you're still online.
Can you hear me?
Yep. Yep, we can hear you.
Oh yeah, those are based on our technical circuit at MOTI, where our engineers, when they design things for.
You just speak a little closer to the mic, Jim.
Sure. Yeah.
There we go.
Yeah. Those TI work was based on the technical circular, which our engineers are required to show the work on how they're adapting our infrastructure for climate change. So that was probably 80 projects that were included in that summary sheets of the bridges and the culverts, information on how they used future climate change in their design for the varying percentages of change that they would have used in their design parameters. The other, like Mel mentioned, an engineer working on from MOTI. Do you know who that engineer was? Do you have his name?
Yes, that was Arm van Mejdel. And he was in on the establishment of our company, Climatic Resources Consulting. And sadly, he passed about a year ago now.
Oh, that's too bad. Yeah.
He was a great guy.
The other, oh yeah. The other made earlier about IDFCC looking at sub-daily, like they scale the daily future precipitation changes into sub-daily for their IDF information. But I'm not sure that just scaling it the way they do it is accurate. And I think the comment was made that they are looking at if sub-daily can be scaled. that's a question for engineers. But I'm not sure. I think I've seen other research or heard of other research where it says that sub-daily, you're going to find more peaks than you are in the daily, probably. So anyways, just a comment.
That is my understanding. And when I've looked at sub-daily for the city of Nelson, it was quite interesting. It was kind of all over the place. And for example, the storm events that caused the stormwater system to be overwhelmed were, in one case, is 8 minutes in duration, where it rained at 135 millimeters per hour. And when you look at that for daily, it was nowhere close to being the highest daily total. So I think it gets hairy when you're into sub-daily. But I think Charles has looked at that in a little more detail. You might have an idea on that.
Yeah, I'm not really there yet to comment too strongly on it, but there is definitely a strong caution when you're trying to take maximum daily rainfall and disaggregate that into sub-daily, because it doesn't really correlate well the farther the timescales go. Get apart.
Yeah, and also just to comment, Jim, on how the particular methodology that you were questioning in IDFCC. I mean, we can, whatever tool is going on, we can always start. There's always a question of whether that's valid, and this is when it comes to again incorporating this uncertainty assessment or sensitivity analysis or whatever we want to call it, checking multiple different tools. Probably that's, at least as a first iteration, that the best way to deal with any kind of, if you're looking at a tool or a model going, is that really correct? I think the best way we can deal with that is multiple tools, multiple sensitivity analysis, and unpacking all the different uncertainties to do with climate change, and then also then relating that to all the uncertainties that have to do with the DFH process. And that's kind of where we're going to go with the second webinar, to try to give kind of relative weight to all these things when considering everything in a big picture.
Yeah, exactly. I think that Mel's presentation pretty much pointed that out, that there's a lot of variable in what data you're using, and whether it's a valley bottom or the mountain top, where your infrastructure is being designed for. So elevation makes a I guess could be incorporated in as well into the data. So yeah, it was all very interesting. Just basically the uses of data and what it's telling you, and maybe what it's not telling you.
Yeah.
One thing, I'll just make a plea for anyone who can influence anybody. The more data we have, the more confidence we have. And unfortunately, it seems to be that there's less and less data available all the time. When I looked at AHCCD data, temperature and precipitation for the Columbia Basin, and put in red squares for missing months when I was looking at monthly and annual, when you look at 100 years of data, there's this, it gets redder towards the bottom, towards the recent. So we definitely, the more data we can get our hands on, the better.
Yeah, and one comment here from Dave Spittlehouse. He's saying that Francis Zwiers from PKIC was talking about this 7% increase of precipitation I guess, intensity per degree increase in sub-daily events. And that's something that I've heard some engineers or some designers use that. It's not too common. I don't know if either of you can comment to that, Mel, if you looked at, just looking at precipitation through temperature in that way. Yeah,
there's a strong relationship between the amount of water vapor in the atmosphere and temperature. So the potential for more extreme rainfall events goes up. I think it's the same number by 7% more water vapor in the atmosphere per degree Celsius. And I believe that a paper that Francis was involved in, and I, for the life of me, forget the first author, but it was 2012. they looked at, I think, 8,000 climate stations worldwide and established that there was that was coincidentally, I think, the same number, 7% increase in one-day maximum rainfall globally when you average it all up. That's what I'm familiar with. And I'm not sure about the sub-daily, but I wouldn't be surprised if it's similar. Essentially, when it comes to water vapor in the atmosphere, what goes up must come down. And the more you put up there, the more it's going to come down.
Yeah. Yeah, if anyone wants to put into this chat, if anyone's using that, I've heard of one designer using that as an approach, as a rationalization. I don't think it's a too common of an approach, but again, just another tool in the toolbox. We have a comment from Aurelia that Mel was also saying that you can check the climatology to inform your use, but also that you can look at the change in future versus the history. So I think that goes to say, in terms of all these, getting a specific number and how the elevation might be coming into play, that's one thing, that's the history. But if you're looking at the change, that only the change, and maybe you're getting your historic values from somewhere else, not that tool, it's a good distinction to make. Exactly.
Yeah, the relative change between your base period and the future is the key number, especially with temperature. And that's, the model projections give us the best estimate of that that's available. But the key thing is that I think some people are charging ahead with the absolute numbers, and you just got to be aware that may not reflect valley bottom conditions for temperature.
Yeah, it's a good thing to reiterate that we didn't iterate at the last series. There's a question here for me, but also, I guess also for anyone who knows about IDFCC. Would you say that IDFCC tool is primarily of use in rainfall-dominated basins? Would this not limit its use in BC with primarily snow-dominated basins? I don't know if I know enough about design flood hydrology to really make a conclusive statement about that. But it's definitely, the smaller the basin, the more useful it is. Otherwise, you're going to get into much more uncertainty with all the other parameters in your DFH and rational rainfall equations. It limit its use, I guess, if you're for sure. I'm not sure if you can have a watershed and say for sure, if it's a relatively small watershed, let's say 40 kilometers squared, if you can for sure say that the dominant flood will never be an intense storm, then I guess that it wouldn't be useful in that. I'm not sure how often or what kind of variation of characteristics that we have in these small watersheds. So maybe someone can comment there or raise their hand, make a comment.
Well, my understanding from the perspective of someone who isn't a hydrologist is I think that the CC-IDF tool is of most use in urban watersheds where it's extremely flashy. What we saw in Anderson Creek is that it seemed to be just by inspection that the RX2, the 2-day rainfall, was what was the discharge was most responsive to. And my hunch is as you go up in scale, it may be RX5 if you're in a larger watershed. But I just have a very qualitative sense for that, and I might be wrong.
And Dave Spittlehouse says, I guess following up, Francis gave a presentation on subdaily precipitation increase at the CMOS conference a week or so ago. Kari, we need a guidance document from PCIC on this. So you got some work, I think. And you're muted.
Yeah, thanks, Dave. I'll take that into consideration. I think what often is the challenge is the application from theory to practice. But if you have any advice on what the shape of that guidance document should look like, I'm happy to work with that.
Okay. Right. So I think sorry, we forgot to look at the time. We're a bit over now, so I think it's probably time to wrap up. We don't have any questions coming in. So thanks everyone for joining, and thanks to Mel and Kari. and hopefully everyone can join us on Tuesday when we do a delve into DFH and case studies. Okay. Thank you.
Thanks, Pat.
Thanks, everyone.